Okay. I'm going to get back to electricity and magnetism this morning after our excursion into light. Now we know light is a transverse wave of some kind. We don't know quite what's waving, but we know it can be polarized, and it has the interference properties that are characteristic of waves. Now, we're going to get back to electricity and magnetism, and then eventually we're going to get to some discoveries where you'll see why I took that excursion into light, and we'll see a certain connection between light and electricity and magnetism. And the first part of that connection was actually made by Michael Faraday. And that's the first thing I want to tell you about this morning, is a discovery of Faraday's. Faraday, remember, in his work on electricity and magnetism, developed the concept of electric and magnetic fields. I mean, his idea was, it's not just that, a charge, say in a certain location over here, acts on some charge in a different location just by some magical action at a distance, that something is actually going on in between those two charges. That the first charge, for example, if you think of just the force between two static charges, this charge 1 that's acting on charge 2 actually creates an electric field around it. And it's that electric field that actually pushes or pulls on the second charge. And similarly, Faraday had that same idea for the magnetic fields. That if you have a current through a wire, okay, we know that it deflects a magnetic compass needle, okay, that will point, around in a circle, going around that current. Well, Faraday thinks that what's happening in that case is that the moving electric charges are creating a magnetic field in that space around the wire. Well, Faraday was also, of course, well acquainted with these discoveries about light that we've talked about. The discovery that light was a wave, and they didn't know what was waving yet, but they knew it wasn't like sound. It didn't have anything to do with the air. If you take of course by this time they're perfectly capable of creating vacuums, right? So they've got vacuum pumps. If you create a vacuum in a container, sound won't go through it, right? You can't send sound through a vacuum because it depends on, a sound wave is vibrations of the air molecules, of the air. If you take the air away, there's no sound. Well, but you can send light through an evacuated container, right? It doesn't matter whether there's air there or not. Light goes right through. So, they knew that light was a wave, but whatever it was waving, it had nothing to do with the air. Okay, there's some physical stuff that's left behind in a container, even if you pump out all the air. And if light was a wave, it had to do with the waving of that physical stuff, whatever that is. Okay, they didn't know what it was. But of course, Faraday also knows that electric charges affect whatever this physical stuff is. Okay, so you have light that is a wave through this medium that they called the ether. Okay, and you have electricity and magnetism that that affect the state of this ether somehow by setting up these things that Faraday is calling electric fields and magnetic fields. So Faraday thought, well, light, electricity, and magnetism, somehow they're all states of this stuff, this ether that we don't really know anything about, that's different from the air. Even if you take all the air away, you still have this ether stuff left behind. Okay. That gave Faraday the idea that if these electric and magnetic fields are certain states of this stuff, and light is a wave through this stuff, maybe there's some connection between electricity and magnetism and light. And so he started looking for that connection. So let's just call this, let's see, Faraday's for now, I'll just call it Faraday's discovery. And this happened in 1845. Now, the only thing he has to go on at this point is this very general idea that there should be a connection between light and electricity and magnetism, because they're all states of this underlying ether. Now, he doesn't know what the connection should be. Okay, he's got a general reason for having a suspicion that there is a connection, but he doesn't know exactly where to start with his experiments. Now, contrast this, sometimes this happens in science, where you've got a general reason to look for a certain connection, a certain effect, but you don't really have any idea what specifically the effect is. So it means there's a lot of different experiments you have to try before you might make a discovery, because you're working a little bit blind here. I mean, sometimes, so that's the nature of this investigation Faraday has to go through. Now, contrast that, for instance, with if you think of, say, Newton's optics, okay, where he's investigating colors. Remember that, where he spreads them out with the prism? Well, after he does his first experiment, where he takes the sunlight and spreads it out into the color spectrum, that gives him the idea that, well, maybe all the colors are in the white light and they're being spread out. Well, that idea immediately leads to certain experiments to test that specific idea. Okay, so, I mean, after Newton gets that idea, he's immediately led to, he knows exactly how to design his experiments in order to test it. So he's got a very specific direction to go in. But Faraday's not in that, happy situation here. He's just in the dark, looking for a connection between electromagnetism and light. Okay, so he starts out looking for a connection between electricity and light. And what he does is he sends electric current through a whole bunch of different kinds of materials. And then, transparent materials that he can also send light through. And then he sees whether or not the light is in any way affected by the electric current. Now, he does this for 8 days, a whole bunch of different kinds of experiments, sending, he's got like liquid solutions with acid and salts in them and stuff that he is, with a battery, he's sending a bunch of electric current through those liquids, and then he shines light in from various directions and sees whether there's any difference between what happens to the light without the electric current and what happens when he has the electric current. Nothing. Okay? Doesn't find anything in any of these experiments. So this goes on for a week or two, doing different experiments every day. All results negative. So he gives up on electricity for the moment anyway, and he turns to magnetism. And he says, well, what he's going to look for, do the same thing with magnetism, basically. Take various transparent materials that light will go through and create strong magnetic fields with magnets that he puts in various orientations, creating magnetic fields through these materials and then shining light through them. And he doesn't want to just test if the direction of the light is affected. He's also testing whether or not he starts using polarized light and testing whether or not the polarization of the light is affected. And again, he does a bunch of different experiments that fail. And then he finally does one that works. Okay, so let me tell you about the one that actually worked. Faraday had discovered a type of glass that had a very high index of refraction. It is a lead borate glass. Okay, so uses lead borate glass. And by high index of refraction, remember what I mean by that is it bends the light, it refracts the light more than most other substances, bends it more. And so Faraday's idea is he's going to take a slab of this glass and send light through it. And he's going to send polarized light through it. So he has a polarizer here. And the light goes through the glass, comes out over here, and he's got another polarizer over here. And then he can shine the light on some screen here where he can see what the brightness of the light is. Okay, so this is the incoming beam. Now, let's say that this first polarizer makes the light vertically polarized here. Okay, so it only lets the light that's waving in the up-down direction through. Okay, so that's what's going into this lead borate glass. Okay, now when Faraday just does this experiment as I've drawn it on the board, nothing much happens. Most of the light makes it through the lead borate glass. A little bit is absorbed. But coming out on this side, you again just have the vertically polarized light. So if you have this polarizer oriented vertically, then it lets all the light through, right? And you get a bright spot on this, this screen here. Well, what Faraday discovered was that if he now puts a strong magnetic field through this glass, let's say he puts it in this direction now. So, strong magnetic field. What's the symbol for magnetic field? B. I heard somebody say it. So I don't have to keep writing magnetic field. I can write B from now on. Okay, when he puts a magnetic field through this glass, in other words, he just arranges powerful magnets that create a magnetic field that is in the direction right along the light beam. What he finds is that the intensity of the beam that makes it through this second polarizer decreases. Okay? It suddenly gets dimmer. Now, what would you do next if you were Faraday?
Wait, are the magnets around the glass or just any part of it?
Oh, well, let's say he has a powerful north, I mean, imagine a big horseshoe magnet here. That's the North Pole and that's the South Pole. Right.
I might like rotate the polarizer at different angles and see what lets more light get through.
Yeah, exactly. This second polarizer, I mean, that's Faraday thought of doing exactly what Troy thought of doing. You rotate this second polarizer and see whether or not you can find a place where this light beam is as bright as it was before. Now, let's say that he rotates this polarizer. I mean, if you look from the direction of the borate glass at the polarizer, let's say he rotates it 30 degrees clockwise and finds that now the light beam returns to its full brightness. What would that tell you? Nick?
That the magnetic field is turning at 30 degrees, the light wave?
Yeah, that the polarization of this light beam has actually rotated 30 degrees by going through this lead borate glass with the strong magnetic field going through it. Now remember that the lead borate glass by itself didn't rotate the light beam at all. Only when you put this strong magnetic field through it, then you get this rotation of the polarization of the beam. Now it turns out that there's a right-hand rule for how the polarization of the light beam gets rotated here. If you put your thumb in the direction of the magnetic field here, your fingers will curl in the direction that the polarization of the light is rotated. Yes?
Now, if he took the glass away and just had the magnetic field.
Yeah, exactly. That doesn't work either. If he takes the glass away, the polarization of the light beam won't rotate. So it does depend on having both. You've got to have the glass and the magnetic field in order to get this rotation. Now, by the way, that right-hand rule that I just told you about, what will happen if I flip this big horseshoe magnet around now? So I change the direction of the field. Troy?
You'll have to move the polarizer in the other direction.
Yeah, he'll have to, it'll rotate the polarization of the light in the opposite direction now. So, now can you think of anything else you would test here? What would you try, any ideas on what you might try next? Faraday had a couple of ideas. Yeah, Daniel.
Could he try and see if the same thing worked with an electric current instead of a magnetic field?
Oh, yeah, he'd actually already tried that. That he had sent currents through various, electrolytic solutions, I mean, liquids, but also even some, poorly conducting solids, and couldn't find any effect. Troy?
We'll try it with horizontal light coming in, or that?
Oh yeah, well you can do that. I mean, if he flips this polarizer, it turns out that the only effect that has is, I mean, you start out with the light horizontal, but it'll still rotate it in the same direction by the same amount. Okay, so but Faraday thought of, one question you might think of is, well, is this some kind of special property of lead borate glass? I mean, does it have to be lead borate glass? Turns out that this was a fortunate choice for Faraday to start with. He started with this glass only because he knew that it deflected light in refraction really well. So he thought, well, maybe it has a stronger effect on light than most other materials, so I should use this, which was a good guess on his part. Now, he did find that this same kind of rotation of the polarization of the light took place in a lot of other different materials too. So lead borate glass is not essential here. It just happens to be it's a nice choice because it rotates the polarization more than most other materials. But Faraday went on to discover that a whole bunch of different materials will rotate the plane of polarization. Even water will rotate the plane of polarization of the light. If you put a strong magnetic field through water and then send the light beam along that magnetic field, you'll see some rotation of the polarization of that light. Now, the other thing that the amount of rotation depends on, that you might guess that it would depend on, is the thickness of this glass, right? I mean, if you made the glass thinner and thinner, you expect to get less and less rotation, right? I mean, obviously, if you take the glass away entirely, you don't get any rotation. So if you take more and more of it away, you should get less and less rotation. And that's exactly what Faraday saw. He found that when he tried to quantify exactly how much the light is rotated, he found it depended on three things. First, the strength of the magnetic field. So the amount of polarization, if you double the magnetic field, the amount of rotation of the polarization will double. Okay, so it's directly proportional to the strength of the field. It's also directly proportional to the thickness of the glass, or whatever you're using here, the thickness of this material. And then the other thing it depends on is just the nature of this material, what material you pick. Troy?
Did you try this with different colors of light too? Or?
Oh, that's a good idea. Yeah, it is color dependent, and I mean not really strongly so, but let me see. I'm trying to remember. Which way does it go? Okay. I'll have to get back to you on that. But yeah, there's either the red or the blue end of the spectrum is rotated a little more than the other. Okay. Now this is an interesting result because it really gives strong evidence in favor of Faraday's idea that there should be a connection between light and electricity and magnetism. That his reasoning was, since both are states of this underlying ether that's everywhere in space, that there should be a connection. And no one had ever discovered a more direct connection than this. I mean, here was a case where a magnetic field is having a direct effect on the light. It's actually rotating, it's changing the angle at which the light is waving. So now, let me see, Faraday actually has a comment about this that I wanted to read to you. Okay, he discovered this after doing 2 weeks of experiments that failed every day. He finally did this experiment on September 13th, 1885, and he wrote in his notebook, "Thus, magnetic force and light were proved to have a relationship to each other. This fact will likely prove exceedingly fertile and of great value in the investigation of both magnetism and light." And then he ended this entry into his notebook with a statement, "Have got enough for the day." So evidently he was ready to quit at that point. So that's a pretty good day's work, actually. Okay. Now, are you clear on this? Because I went through it a little fast. So you understand what's happening here? That the light starts out shaking in this direction, and then it turns as it goes through this glass. And the amount it turns just depends on the strength of the field, the thickness of the glass, and the type of glass that you use. Now this is actually, I should mention that, I'm going to get to in a moment this discovery of a connection between light and magnetism that Faraday made would play a role in motivating further investigations into that connection, which will lead to another big discovery. But even aside from that big discovery I'm leading up to, there's several applications of this effect that Faraday discovered. For example, astronomers actually look at the light from distant stars, galaxies, and they can use this effect to actually estimate the strength of magnetic fields in in distant galaxies and quasars. So knowing the relationship between the magnetic fields and polarization of the light actually allows them. I mean, I don't know exactly how they do that, but it does allow them to estimate magnetic fields, for instance, in quasars. So that's one application of this. Another slightly more earthly application is that this effect that Faraday discovered is actually used now to estimate the chemical compositions of certain materials. Let's say you have a material which is a mixture of two different chemicals. Okay, and you know how much each of those chemicals separately will rotate the polarization of the light when you put a magnetic field through it. Well, if you've got some mixture that you don't know the composition of, you can just shine light through it, put a magnetic field on it, shine light through it, and by how much it shifts the polarization of the light, you can estimate what the chemical composition of that mixture is. So they actually use this to estimate, to analyze chemical mixtures. Oh. Okay. Okay, now I want to go on to if there's no questions on that, let me go on to the next major physicist that I want to tell you about. And his name, which we speak with reverence, is James Clerk Maxwell. And Faraday was probably the greatest experimental physicist of the 19th century. Maxwell, I think, was the greatest theorist. And you can see that he had a fairly short life, actually. He I believe he died of stomach cancer at the age of 48. And he would have accomplished a great deal more if he had lived longer. But what he did accomplish was first to complete the theory of electricity and magnetism in a way that I'll tell you about, and then actually put the finishing touches on the proof of the atomic theory of matter, too, which we'll hopefully learn about at the end of this year, assuming I get that far. So the two major developments in the 19th century were electricity and magnetism and the atomic theory of matter. And Maxwell made enormous contributions to both. So he was, just from that point of view, he was the leading physicist of the century. Now, so the first thing I want to tell you about is his contributions to electricity and magnetism. And I can't tell you as much as I've told you in some other cases with the guys we've covered, because at this point, the subject gets more complicated mathematically. And in contrast to Faraday, Maxwell was a brilliant mathematician. Faraday never really learned that much mathematics. He was an absolutely brilliant experimentalist. And he came up with crucial new concepts like the fields that we've talked about. But he never knew much mathematics. I mean, you recall I told you his story. As he was growing up, I mean, he was raised in the poor section of London, and his father was a blacksmith. And he never had much of a formal education. And he never really learned that much mathematics, which did restrict his contributions to electricity and magnetism, because he never came up with the equations. He came up with the ideas, and he would quantify them to some extent, but he never cast the full theory in mathematical form the way Maxwell would. Now, I mean, Maxwell was quite the opposite. He had a very good, solid education, and became interested in mathematics early and learned the subject extremely well. So he had a great advantage over Faraday. And when he got interested in electricity and magnetism, he had this ambition of creating a consistent mathematical theory. But he wanted to start from what Faraday had done. The first thing he did was read all of Faraday's, all of his published papers, and study Faraday's physical ideas very, very carefully. And he came to the conclusion that the right way to approach electricity and magnetism was not to start with the mathematical theories that were being proposed by a lot of the French and German physicists, but to start with Faraday's physical ideas and his experiments, and then see how to cast that into mathematical form. So that's what Maxwell did. Now, when Maxwell studies electricity and magnetism, he notices a certain inconsistency in the ideas. He actually discovers that there's an effect that's been overlooked, that there's a missing term in these equations that he's trying to formulate that will complete the theory. And that's the first thing I want to tell you about, is Maxwell's missing term. And I'll say a few things about exactly how he discovered it later, but first let me just give you a physical idea of what the effect that Maxwell discovers. Okay, so call this that's probably a really bad title, but let's let me explain physically what this effect is that no one had noticed before, that Maxwell discovers is necessary in order to have a consistent electromagnetic theory. Let's say we have two metal plates here, and we attach wires to these plates, and to a battery. Okay, so the positive end of this battery is connected to this plate on the right and the negative end of the battery to this plate on the left here. Now what's going to happen? Well, current's going to start flowing, right? And it's going to charge up these plates. So this plate is going to be charged positive and this plate's going to be charged negative. Now, of course, after the battery's been hooked up for a while, the current stops. I mean, the battery has a certain amount of power. It can charge these plates up to a certain amount and no more, right? So the current will flow for a while until these plates are fully charged up, and then it'll stop. Now, while the current is flowing, what if you put a magnetic compass out here? What would you see? Daniel?
See the needle deflect away from the current.
Well, you'd see the needle deflect. Let me see how the current is going to be, say, flowing in this direction. So what direction? It's going to set up a magnetic field, right? What direction is the field going to be in? Nick?
Out of the board on the bottom of the wire into the board.
Yep. Yeah, so all you have to do is put your thumb in the direction of the current, right? Your fingers curl around in the direction of the magnetic field. So you're going to have a magnetic field that is into the board up here and out of the board below the wire. Okay, so there's my B field. Now you're going to have, okay, the same thing is going to be going on over here on the other side of the negative plate, right? You're going to have also B field rotating around in circles around this wire. What's going on in there? Now, does this magnetic field that is going in circles around the wire just suddenly, abruptly stop at the, millimeter that the wire stops and goes into the plate? Or is there some magnetic field in between those two plates? And if there is a magnetic field in between those two plates, what's causing it? Since there's no flow of electric charge between these two plates. Okay, well, turns out that there is a magnetic field in between these two, the plates, and it's just like the magnetic field outside the plates. It's into the board, up above the plates, out of the board as I've drawn it, below the plates. Exact same sort of magnetic field in between the plates that you find outside the plates going around the wires. But it's caused by, it has a different cause. What is going on in these plates? There's something going on in here. There's just no electric charge flowing, but there is something going on. Remember, positive charge is piling up on this plate. Negative charge is piling up on this plate. So if you think in terms of fields, what's going on in between the plates.
They're
Yeah.
trying to attract.
Well, they're definitely trying to attract. But I mean, we have them firmly held in place, so they're not moving. But now, if you draw the E field, I mean the lines of the E field here, okay, they go from positive charges to negative charges, right? So we've got an electric field, certainly, in between the plates. Now, what's happening to that electric field? The charges on the plates, I mean, if current is flowing, the charges on the plates are piling up, getting bigger and bigger, right? So what's happening to the E field? Stronger and stronger. Okay, it's not just an E field that you have between these plates. It's a changing E field, right? You have an E field that starts out at 0. Okay, when you just hook up the battery, the current flows to charge up the plates, and this E field ramps up. It gets bigger and bigger. So you've got a constantly increasing, changing E field in between these plates. Okay. Oh, I'm running over, aren't I?
Yeah.
Oh. Okay, let me quickly wrap up, and then we'll pick this up this afternoon. But basically what Maxwell discovered was that a changing E field causes a magnetic field. And so there's two ways to cause this kind of circulating magnetic field. The Ampere discovered the first. That was just, a current flowing through a wire causes this circular magnetic field around the wire. Maxwell discovers a completely different way to make the exact same kind of field. That you can do it with a current, or you can do it with not just an E field, but a changing E field. Okay, so I'll explain that more this afternoon.